All right. All right, so before we get started, there was a correction on one of the very last example from yesterday. I put the wrong values. We plug in the X and Y. These are the correct values. I am one of those. I try to fit everything on one piece of paper, and I just ended up writing down the wrong values when I calculated them. So these are the correct values. So it's the very last example. And again, thank you for pointing that out because I completely missed it. All right. And okay, so make sure. All right. All right. So today we are going to look over finding the volume by slicing. And it's kind of in three parts. So this is part one. So let's say if you wanted to find the volume of a rectangular building. Oops. And make that eye a little neater than that. So let's see if we can kind of sketch a rectangular building. So it would kind of look like this. Kind of shade in the base just to clear it up. Okay. So we know that that volume of a rectangular building will be the length times the width times the height. I'll put lowercase w and h. Since the uppercase has a different meaning. And put a lowercase l. Get another eraser because this one is worn down. Here we go. Make this a little bit neater with an actual working eraser. There we go. There we go. Okay. Same thing if you had a cylindrical shaped building. that volume will be pi times radius squared times the height. Okay. You'd find the area of the base times the height for both of those. That area of the base is what we call our cross-sectional areas. Kind of make that a little neater. Okay. So what if we had a more non-traditional shape? Okay. It's not one we have just a ready-made formula for the volume just waiting. Okay. So what if you wanted to find the volume for a loaf of bread? And no, I cannot draw, so this is as close to a loaf of bread as you're going to get from me. I am horrible at drawing, so you will discover that very quickly. Okay, so just the volume of a loaf of bread. And you can kind of just have the front and the back and kind of the rest of it in between. Okay, so with this, all we're going to do is just like up here, we're going to pick a cross section of this piece of bread. So just a little cylindrical cross section. And we're going to basically slice it out. So if we take that little slice out and just kind of draw it a little bit bigger. And let's say we decide to put it on a number line. So the width of that little slice out of there, well, the left endpoint, that'll be your x sub I minus 1. And your right, that'll be x sub I. So if you made I equal 1, that'll be from x sub 0 to x sub 1. If you made I equal 2, that'll be from x sub 1 to x sub 2. So if we take that odd shape and just snatch out that cylindrical piece from it, then we know that the volume for just that piece, well, not equal to, it's approximately equal to the area of the cross section times the width, because it depends on how wide we have it. Oops, make that a little neater. And that is your width there. Okay. I'll leave it as height. I'll leave it as width. Okay. So for this one, if we get that and just kind of lay it sideways, we have the area of the cross section, which in that case would be your height and your width. Since they're multiplied, they can be interchangeable. All depends on which direction you have it. Okay. Okay, so we know that each of those little cylindrical slices has a width or height, depending on which direction. Actually, I'll change that back to height. I don't want to switch it up both ways. That'd be a little just keep it one way, just to avoid making it more confusing. The width of x sub I minus 1 to x sub I. Okay. And we also know there exists some value c in the interval of that area. Where we know that the area at that exact value is really close to the overall area or the approximate area. And we'll call that C sub I, because that would change with each individual one. Okay, know that it's really close to the approximate area. Okay, so the volume of that slice is going to equal the height, again, if you turn it sideways. But either way, that would be your cross-sectional area. Times your width, if you turn it that way, which in that case would be delta x. Okay, and that becomes your volume is approximately equal to A of C sub I times your delta x. Okay. Now, if you wanted to kind of help visualize it, if you get that and kind of turn it on its side, that's the area of your cross section. This is your width. Kind of like we did with in Calc 1, when you have your limit and you just take the limit of the area underneath your function and you put a little rectangle in there, and then you just make the width of that rectangle smaller and smaller and smaller. And then as the number of rectangles increase, you get really, 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 really close to the actual area of that function. This is the same idea. And we'll continue on the next page. Make that go. All right, anyone still writing? All right. So as the slices increase, okay, so the more slices we put in there, the smaller the width. Because if we put in 5 slices, it's pretty wide, but if we put in 100 million cylindrical slices, they have to be pretty narrow. So we know as the slices increase, your delta x approaches 0. That width approaches 0. So the distance between x of I minus 1 and x of I gets smaller in order to fit all of those cylindrical shapes. So we get closer and closer to the actual area. Not area, volume. Okay. So it's really the same idea that we did with integrals before. The only difference is we're applying it to kind of odd shapes now. That means the volume is equal to the limit as the number of rectangles approaches infinity of the sum from I equals 1 to n of the volume of each individual slice. Or notice that this is just the limit definition of your integral from a to b of the area of the cross section times your width. I mean, you can use this if you want to, but I would prefer this one. It's a little easier. Remember, this is your cross-sectional area. All right, anyone still writing? All right, so let's go ahead and look at an example. Okay, so what if we assume that a half cylinder shaped object and let's say that object kind of looks like this, where you have a half cylinder oops. Okay, so we know that this object has a radius of 3. And if we lined it up on a number line from x equals -2 to x equals 4. So if we know the radius is 3, what is the volume? Of this cylindrical shape? And a lot of times they'll give you a picture of the image, so it'll look a whole lot better than mine. Okay, so since it's a cylindrical shape, you see that this half cylinder, the cross-sectional area would just be this half a circle. Okay, so we know that the area of a circle is pi radius squared. That's just for reference. So that means the cross-sectional area which is half a circle, that's 1/2 of pi radius squared. Okay, so we know that the volume is equal to the integral from A to B of your cross-sectional area times your width. So we know that our interval is from -2 to 4. So that's the integral from -2 to 4 of our cross-sectional area, which is 1/2 pi radius squared with respect to x. So we know that our radius is not one of our independent variables because they gave us the actual radius. We know that the radius is equal to 3. So yeah, from -2 to 4 of 1/2 times pi times 3 squared. So if we simplify that, that just becomes 9 pi over 2, which is a constant. We can factor that out. Oops. And you can put dx or you can put 1 dx. Completely up to you. Okay, so if we integrate this, that gives us 9 pi over 2 times the integral of 1, which is just x. And that's from -2 to 4. Right. So after we integrate it, since it's a definite integral, we go ahead and apply the fundamental theorem. So that gives us 9 pi over 2. Plug in our upper bound, which is 4, minus plug in our lower bound, -2. That gives us 9 pi over 2 times 6. Well, 6 divided by 2 is 3, so that just gives us 27 pi if they wanted the exact value. And they'll usually tell you the exact or decimal approximation. All right. Any questions on that one? Anyone still writing? Right. Okay, so let's say, suppose we have a dome. It has a circular cross section. With the outline y equals plus or minus the square root of 45 divided by 2 times 90 minus x. For the interval between 0 and 90. Okay, so kind of a view of that. Five to 90. Kind of the bottom half of this goes to negative 45. Well, we know that the dome is above ground, so this is the only part we're going to kind of worry about. So let's say if we want to find the volume of the dome in cubic feet. Okay. Now this one, you want to be careful on because the radius changes as you approach 90. Okay, so we know that as you get closer and closer, the radius, which is just this distance here, that's your radius. Of course, it goes in the other direction too, but we're just worried about above ground. Make that a little bit neater. Here we go. So we can see here that the radius is dependent on your value of x. The radius changes depending on what x is. So it's actually r of x is equal to, and since we're just worried about above ground, we're just worried about the positive 45 divided by 2 times 90 minus x. So that means the cross-sectional area would change depending on how far in we go. So area equals the pi times the radius squared now becomes, the area is equal to pi times the function of your radius squared. Okay, well, we know the function of the radius, and depending on the x value, is the square root of 45 divided by 2 times 90 minus x. So that means that area, your cross-sectional area, would be pi times the square root of 45 divided by 2 times 90 minus x squared. Excuse me. Well, luckily for us, we know the square and the square root cancel each other out. So the area is equal to pi times 45 over 2 times 90 minus x. Okay, so that area, we could rewrite that as a function of x now. So we could say the area, or we could rewrite it as a of x. Either way works, whichever one you're most comfortable with. So we know that our volume will be equal to the integral from x equals 0 to 90. Of your cross-sectional area. I'm just going to go ahead and combine those two factors. So that's 45 pi over 2 times 90 minus x dx. Now, you can do it a couple of different ways from here. If you want, you can factor out 45 pi over 2 and then take the integral of both of those terms, or you can distribute and do it all together as one, completely up to you. I'll go ahead and distribute just to show that one, even though the other way probably would have been easier. Okay, so the volume is equal to the integral from 0 to 90. So if we take, well, actually I'll factor out the pi just to keep from having to write it down over and over. So that's 45 divided by 2 times 90. It should be 2025 minus 45 divided by 2x. Okay, so from there, we just go ahead and integrate each one of those terms. It's pi times the integral of 2025 x minus 45 over 2 times the integral of x, just x squared over 2. And that's from x equals 0 to 90. Okay, so now we can go ahead and apply the fundamental theorem. Okay, so that volume is equal to, and again, I'll go ahead and leave pi on the outside. Okay, so we go ahead and plug in our upper bound. That's 2025 times 90 minus, and I'll just make this 45 over 4. Times 90 squared. Minus, I would go ahead and plug in our lower bound, but we can see that's 0, but I'll plug it in anyway. 2025 times 0 minus 45 over 4 times 0 squared. All right, we can see those just disappear since they're equal to 0. So when the volume is equal to pi times 2025 times 90 is 182,250. Bring that 1 out a little bit more. Minus 90 squared times 45 divided by 4 is 91,125. Which actually gives us 91,125 pi, which would be your exact answer if they want the exact answer. Or if you plug that into your calculator, you'd get 286,278 approximately. Cubic feet. So again, it just depends on what form they want it in. They'll usually tell you, present your answer in the as a function of pi or as an answer of pi. Then you leave it like this one. Or they may say round to the nearest whole number, and then you'll leave it like that. And they're usually pretty good with telling you what form to put the answer in, but sometimes they'll, I guess, forget to add it in. So if one doesn't work, then you can try the other. All right, any questions on that one? Yes.
For the part where we start finding the volume, is the reason why we chose like the positive version of the square root because we're looking at it from above ground?
Yep, because if you have the positive of the square root is here, the negative be down there. And because we're looking at a dome, that's why we're only looking at the above ground part of it. That was the only reason why. You're welcome. Oh, yes.
So why did we do, why did the area become IR x squared?
Oh, because the area is just a cross-sectional area. And that cross-sectional area, which is this part here, that changes depending on the value of x.
Okay.
So as x increases, that area gets, cross-sectional area gets smaller. So we can't just say the cross-section or the radius is just this one value, because it kind of changes little by little. Yep, exactly. So you only have to do that if the radius changes. If the radius is constant throughout, like the previous problem, they said the radius is 3, then you already know you don't have to worry about the extra stuff. Does that make sense?
Yeah.
Okay. Cool. All right. Any other questions on this one? All right. Oops. All right. Anyone still writing? All right. So let's say, for example, if a solid is formed by rotating the region under a curve, let's say y equals 1/3 times the square root of 16 minus 4x squared. Let me clean that 6 up a little bit. About the x-axis. So we want to find the volume in cubic centimeters. Okay, so if we were to graph that, we'd rotate the region y equals 1/3 times the square root of 16 minus 4x squared. So we know this rotates between 2 and -2 just by graphing it. And again, graphing it is just the easiest way to get a visual of it. Okay. So now all we're going to do, since it said it's rotating about the x-axis, it's rotating about the x-axis. Oh, that was a messed up looking rotation. There we go. That's even worse. Okay, so we know it's rotating this way. Now, the reason we knew that these points were at 2 and -2, I'll do that. If you didn't graph it, we know that's where y is equal to 0. So that means we know that's where 1/3 square root of 16 minus x squared is equal to 0. So if we multiply both sides by 3, that cancels out and becomes 1. This side, 3 times 0 is still just 0. That means where the square root of 16 minus x squared is equal to 0. Or if we square both sides, we still end up with 16 minus x squared is equal to 0. So if we add x squared to both sides, we have 16 equals x squared, or x squared is equal to 16. Oh, forgot my 4. Sorry, I knew that would have threw my answer off a little bit. That should be 4x squared, not x squared. I'm looking like something's not right. My answer should be different. That's why. That should be minus 4x squared. There we go. So we add 4x squared to both sides. We have 4x squared equals 16, or 16 equals 4x squared. Divide both sides by 4, we get the x squared is equal to 4, which gives us x is equal to 2 and negative 2. Okay, so that's how we knew that these 2 points were at 2 and negative 2. That means the area from negative 2 to 2 of our not the area, the volume from negative 2 to 2 of our cross-sectional area with respect to x and we know that our cross-sectional area is pi radius squared. Okay. But again, it all depends because that cross-sectional area varies depending on the volume, not the volume, the value of x. That means that cross-sectional area is just pi times the function of the radius squared from negative 2 to 2. Oh, yes.
So why did the pi come off?
Oh, we just factored it out. That was the only reason. Now, the reason we didn't do like before and say half times pi times the radius squared is because we're not just looking at this one, we're looking at the fact that it's rotating. So it started off like this, but the fact that it's rotating means that the radius changes all the way through for an entire circle. Okay. So before we were just looking at the top half of it. So that's why we took in half of it. Which means that for this curve from negative 2 to 2, and we can bring the pi right on out to the front, we'll get a different value of y for each x. So we know that our radius all depends on the value of x. So that's the square root of 16 minus 4x squared times 1/3 squared. And again, the square and the square root cancel each other out. So that's just pi times the integral from -2 to 2 of 1/3 times 16 minus 4x squared, because the square and the square root canceled out. Oh, it actually should be 1/9. Glad I caught that. Because this square cancels out here, but this is still squared. So we have 1/9 because it's the square of this entire thing. So it should be 1/9. And then that square and square root cancels out. Okay, so again, that 1/9, you can go ahead and factor that out just to get it out the way. Or you can leave it, up to you. But I like to go ahead and factor that right out to the front. Times the integral from -2 to 2, 16 minus 4x squared with respect to x. It is in simplest of form possible. Then we can just go ahead and integrate each individual term. Why did I put the pi over 9? I meant to put it on the integral. There we go. So the integral of 16 is 16x. So we have pi over 9 times 16x minus 4 times the integral of x squared, which is x to the third power over 3. And that's from x equals -2 to x equals 2. I'll finish on the next page. Trying to squeeze it all on there, look messy. Okay. So from here, we're just going to go ahead and apply the fundamental theorem. All right, anyone still writing? All right. Okay, so we apply the fundamental theorem. That gives us pi over 9. Go ahead and plug in our upper bound. So that's 16 times 2 minus, we'll go ahead and combine those to just 4 over 3 times 2 to the third power minus, we'll go ahead and plug in our lower bound. We have 16 times -2 minus 4 over 3 times -2 to the third power. Okay, so we have our pi over 9 times 32 minus 2 to the third power is 8. 8 times 4 is 32, so we have 32 over 3. 16 times negative 2 is negative 32. But as soon as we distribute that negative 1, it becomes positive 32. Negative 4 over 3 times negative 2 to the third power. Negative 2 to the third power is negative 8. Negative 8 times negative 4 is positive 32. So we have positive 32 over 3. But if we distribute that, it becomes negative. So if we go ahead and combine like terms, we end up with 128 pi, well, 128 divided by 27 pi cubic centimeters. That's if they want the exact answer. But if you plug that into your calculator, you should get around 14.89 cubic centimeters. And again, they'll usually tell you. Any questions on that one? All right, anyone still writing? Okay. Now, a lot of those problems could also be solved using what's called the disk method. So this is kind of part 2. Okay, so if you remember, it all kind of revolves around the fact that the area of a circle is pi radius squared. And the volume of a cylinder is pi radius squared times height. Okay, but instead of a cylinder, what if we get one that's a little bit thinner and say the volume of a disk? Because a disk is just a very narrow cylinder. Which is the cross-sectional area times the height. Okay, so if we did get that disk, the radius of that disk would be there, and the height of that disk would be here. Just to kind of help give you a visual. So let's say if we get that disk, or that cylinder rather, and we kind of get the cylinder and twist it sideways. We put it on our XY axis. Trying to draw this as symmetric as I can. There we go. That's not too bad. actually pretty good. Shocked. I probably can never do it again, but so again, if we take just a disk out of this cylinder, so what if we take this and we take just a disk out of here? So we're not going to look at the whole thing, just that one disk that we take out. So we know the width of that would be your delta x, which is your x sub I minus 1 minus x of I. Okay, and the radius of that cylinder would just be your radius function of x, or in terms of x. Okay, so your volume of this cylindrical solid would be approximately equal to the sum from I equals 1 to n of pi times the radius function squared, since that's our radius squared, times delta x. So if we made all of these disks and we took the sum of all of those disks and we added them together, okay, so just like before, the more disks that we slice out of there and add together, the more accurate our volume approximation would be. Which means as delta x approaches 0, the more accurate our approximation. Oops, here we go. I hate these glasses. They get dirty every 10 minutes.
The China Street Journal, which is what.
Okay, so that means if we wanted to find the approximate volume of this disk or this cylinder, a solid of revolution, then that'll be approximately equal to the limit as n approaches infinity, because we want to be able to get as many of those little slices out of there, those little disk slices, of the sum from I equals 1 to n pi times the radius function squared with respect to x. Okay. Well, all of this is just the limit definition of an integral. So we could just rewrite that as the volume is equal to pi times the integral from a to b of our radius function squared with respect to x. And this is just our disk method formula. So this is kind of just a general explanation. The actual proof is a whole lot longer and not really necessary. That's why I didn't worry about going over the actual proof. All right. Anyone still writing? Okay. Now you have two different versions of this formula that you'll be using, and they're pretty. Oh yes.
So what's the difference with like slicing the value and this method formula?
Oh, I didn't hear you.
I said, what's the difference from slicing the value and then the disk method formula?
Honestly, they both have the same concept. It's just if you have a cylindrical form where you can slice out a disk, you can use this method. But if you want to use the other method also, you could, because the first method was for really any odd shape.
Okay.
All right, does that make sense? Okay. Now, the two different versions, you have the vertical revolution and the horizontal revolution. So if you have the horizontal axis of revolution, that's just stating that if you get your cylinder, and a lot of times you may start off with a half cylinder and it revolves around, it revolves around the x-axis. So if you start off kind of your half cylinder, let's say we're just looking on some interval between A and B. Where, of course, the width of all of your disks inside of there is just your delta x. Then that volume is equal to pi times the integral from A to B of your r of x squared with respect to x. Okay. Where if you revolved it around the x-axis, you just get a complete cylinder. But if you have a vertical axis of revolution, pretty much an identical formula. The only difference is with respect to y. So up here, x and y axis. And if I'm trying to draw sideways, I have enough trouble drawing the regular way. There we go. And that's from the interval from C to D. Where every disk we slice out of there is now your delta y.
Plus,
So this from your volume would be pi times the integral, I swear that little integral and interval mix me up every time. From C to D, r of y squared with respect to y. Ooh. All right, oh, still writing. All right, anyone still writing? Okay. Okay, so let's say, for example, we wanted to find the volume of the solid formed by revolving the region bounded by the graph f of x is equal to the square root sine of x and the x-axis. For the interval from 0 to pi. About the x-axis. Okay, so this one, just to kind of give you a visual, we take the square root of sine of x between 0 and pi would kind of look like that. Make my 1 a little more like a 1. And if we kept going, it would just look like that. But we're only worried about 0 to pi. Okay. Now in this case, again, we can see that our radius would change with each one. So in this case, our f of x is equal to our radius function, which is the square root of sine of x. Plus, when you see about the x-axis, we know which one we're going to use. And when they tell you about the y-axis, you know it's going to be flipped sideways. So know that volume is equal to pi times the integral from a to b, your radius function squared with respect to x. All right, well, that gives us pi times the integral. We know for 0 to pi, we know that is our a, and that is our b. 0 to pi of our radius function, which is the square root of sine of x squared with respect to x. Well, luckily, square and the square root cancel each other out. That's just pi times the integral from 0 to pi of sine of x with respect to x. But we know the integral of sine is negative cosine. So we have pi, and we can replace this with negative cosine of x. And that's from x equals 0 to pi. From there, we just apply the fundamental theorem. So we have pi times, plug in our upper bound, it's negative cosine of pi, minus, plug in our lower bound, negative cosine of 0. Well, we know cosine of pi is negative 1. So this is pi times negative 1. Minus cosine of 0 is just 1. So it's minus negative 1. So you could just say 1 plus 1. Or just 2 pi. All right, any questions on that one? Right. Okay, so let's say for this one, we wanted to find the volume of the solid formed by revolving the region bounded by f of x equals 2 minus x squared and g of x equals 1. About the line y equals 1. Okay. So again, graphing it a lot of times helps. Okay, so what if we have okay, so if we have f of x equals 2 minus x squared. So if we get negative x squared, that's just x squared flipped across the x-axis, plus 2 means we shift that graph up 2. So that means our graph kind of looks like this. Now g of x equals 1, same as saying y is equal to 1. It's just a horizontal line through 1. Let me move that 1 out the way a little bit. Okay, so this is just g of x is equal to 1. So we're looking for the volume of this region. These a little shorter, give me a little more writing room. Here we go. Okay. Now, first thing we have to do is we have to find our, well, we can do this second, doesn't have to be first, but the first thing I would do is just find the interval. Okay, so we know the interval is going to be right between there. Okay. So we know that represents our region, so we have to find out where does f of x equal g of x, because that's where they intersect. Okay, so that's where 2 minus x squared is equal to 1. That looks like a z. Let me rewrite that. Okay. So if we add x squared to both sides and subtract 1 from both sides, we'd end up with x squared is equal x squared minus 1 is equal to 0. So if we add x squared and then subtract 2. Okay, so you can use either square root property or you can do difference of squares. Up to you. whichever method you prefer. Okay. So using difference of squares, we know this is just x plus 1 times x minus 1 equals 0, which means this is true when x is equal to -1 and +1. So we know this is our interval. Okay, so we know this. I'm gonna make a quick little sketch here. So we know right along where g of x is equal to 1. We're going to revolve it around the line y is equal to 1. Okay, so that means we're going to take that section and just flip it across y is equal to 1. So that means if we take the volume of our f of x, remember this is our f of x, that gives us the volume of everything all the way down to the x-axis. Now our g of x is y is equal to 1. So we know that if we take our f of x, or our region rather, is f of x minus g of x, not region, radius function. So used to using r for region. Because we take our function here, and that entire interval down to the x-axis, and we subtract it from 1, that gives us our radius function. So our volume is equal to pi times times the integral from a to b of your radius function squared with respect to x. Now before, like I said, we had all of them on the x-axis, so we didn't have to worry about doing that. But because this one was raised up and it's revolving around x equals 1 now we have to kind of shift it a little bit. So when our volume is equal to pi times the integral from -1 to 1 of f of x minus g of x, you can put that in there or you can calculate it on the side, completely your choice. I'll go ahead and do it on the side so we can kind of cut back on some of the steps. R of x is equal to f of x minus g of x. Okay. Well, that gives us 2 minus x squared minus 1. So we have that 2 minus 1. That just gives us 1 minus x squared. Make that a little bit neater. Here we go. Okay, so it gives us 1 minus x squared with respect to x. So we might as well go ahead and simplify that over here. So 1 minus x squared squared, that's just 1 minus x squared times 1 minus x squared. Okay, so if we do the FOIL method, and I'll just write out FOIL here. Our first is 1 times 1, which is 1. Bring that down a little bit. Our outer is 1 times negative x squared, which is negative x squared. Our inner is 1 times negative x squared, which is negative x squared. We combine those, we get minus 2 x squared. And our last is negative x squared times negative x squared, which is positive x to the fourth. So our volume is equal to pi times the integral from -1 to 1. And we can replace this with 1 minus 2x squared plus x to the fourth. With respect to x. And I'm not going to finish it on this page, so we'll continue on the next one. All right, anyone still writing? All right. Get a few more sheets of paper. Here we go. Right where we left off, so we have pi times the integral from -1 to 1, 1 minus 2x squared plus x to the fourth. There we go. Okay, so now we just go ahead and find the integral of each individual term. It's equal to pi times the integral of 1 is just x. Minus 2 times the integral of x squared, which is x to the third power over 3, plus the integral of x to the fourth power, which is x to the fifth power over 5. That's from x equals -1 to 1. So now we go ahead and apply the fundamental theorem. And let me give that a little more room. That tends to expand pretty quickly. Okay, so we go ahead and plug in our upper bound. So that's 1 minus, we can just combine that and make it 2/3 times 1 to the third power. Save on writing. Plus 1 to the fifth power over 5. Minus, we go ahead and plug in our lower bound, which is -1. Minus 2/3 times -1 to the third power. plus -1 to the 5th power over 5. Okay, so we know that our volume is equal to pi times 1. Well, 1 to the 3rd power is 1, so that's just 1 times -2/3, which is -2/3. 1 to the 5th power is just 1, so that's just plus 1/5. You have minus, so we can go ahead and distribute that negative to each term. You have -1, distribute that negative, it becomes +1. Minus 2/3 times -1 to the 3rd power. -1 to the 3rd power is -1. -1 times -2/3 is +1. We distribute this, and it ends up right back at -2/3. Plus -1 to the 5th power divided by 5. Well, -1 to the 5th power is -1. So that's -1/5. But we distribute this -1, makes it positive. Then from here, it's just combining like terms and simplifying. So if we go ahead just to make it quick and combine our whole numbers. So it's 2. And combined our fractions with a denominator of 3. -2/3 minus 2/3 is -4/3. Plus 2/5. And if they're asking for the exact answer, then you can go ahead and just go through it. If they're asking for a decimal approximation, you can just plug those in and go from there. But let's give us the exact answer. So our volume is equal to pi. And our least common denominator is 15. So we can rewrite 2 as 30 divided by 15 minus, multiply both of these by 5, so that's -20 over 15, plus multiply this by 3 over 3, that gives us 6 over 15. Okay, so 30 minus 20 is 10. 10 plus 6 is 16. That gives us a volume of 16 pi over 15. And again, that's if they're asking for the exact value. All right, any questions on that one? Okay, anyone still writing? All right. Okay, now part 3 of 6.2. Is the washer method. And really, that's just kind of a variation of the disk method. because it has the same concept. Where the disk method is just a solid disk. Whereas the washer method is a solid disk, but kind of a hole in the middle. Okay. Now the difference between the formulas really isn't that big if you compare the two. So remember, for the disk method, the volume equals pi times the interval from a to b of our radius function squared with respect to x. Now that represents if you have a solid revolution. Okay, so that represents a solid revolving about an axis. Okay. Now, it didn't say x-axis because, as you saw in the previous problem, sometimes it can revolve around y equals 1 or something like that. So there's an axis somewhere, but it's not always the x-axis. So it's revolving around an axis in the same direction as the x-axis. So it could be the x-axis, or it could be y equals 1 or y equals -3, but it's going to be in the same direction as the x-axis. Now with the washer method, we can see that the disk has an open center. So if the disk has an opening in the center, then visually how that disk would look if we were to draw it on the x-axis, and this is going to give me trouble, it always does. Trying to draw this. Okay. Kind of shade that in a little bit. Let's say this one, kind of make a dotted line there. So that hopefully kind of looks like a disk. Man, I cannot draw to save my life. Each semester reminds me of that. So think of that as a disk, but right around here, you have a hole kind of in the middle. Oops. Okay, so how we're going to do this one is, you notice if you have your disk, you have the radius of the entire thing. So we'll have that as our R of x. But we also have the radius of that missing hole in the middle. We'll make that our lowercase r of x. Make that a little clearer. There we go, R of X. So now we're just looking for the the volume of the entire thing minus that hole in the middle. So that volume is just going to equal the same disk method, but it's going to be the outer radius squared minus the inner radius squared with respect to x. And this is our washer method formula. Excuse me. Yes.
For the inner radius,
Mm-hmm.
where are we really looking at? Is it the entire shaded little circle?
Yes, but the circle on the inside revolves around this axis. We're just looking for the radius, and the radius is just the distance from that axis of revolution.
Thank you.
You're welcome. Yes.
So are you not trying to find like the outer like crescent as well, or no?
Yep, that's our radius for the entire thing.
Okay.
Yep, so we're going to take, yep, so it's kind of like if you think of a donut, if you want to find the volume of that donut, then you use a formula to find the volume of the entire thing minus the whole. Yep. Right. So let's say, for example, if you want to find the volume of the solid formed by revolving the region y equals square root of x and y equals x squared about the y-axis, and then about the x-axis. So again, graphing can be your best friend, because just looking at this, you kind of don't know where to start, but if you graph it, it can help a little bit. And yep, I'll do both. I was going to just draw one, but I'll draw both graphs. little smaller so I can fit all of them on here. Okay, so we know this graph y equals x squared kind of looks like this. So we have our x and our y, and this is y is equal to x squared. It's kind of one of our common graphs. And if we take the graph on our x and y axis, graph of square root of x kind of looks like that, give or take. So we are going to take both of those graphs and put them on the same plane. Bless you. So if we take y equals x squared, on this side of it, I'm just going to kind of draw it, dot it, and then finish the rest of it solid. If we take y equals square root of x, we know that we're looking at y equals square root of x right here. So we see our region is right there. So we got just this shape and we revolved it around the x-axis. So we kind of got this and spun it around the x-axis. Just imagine that just spinning around the x-axis. You would have a hole right there. So we know that hole right there will be right where they intersect. So we have to find out our interval, and that will give us the intersections. So we have to find out where square root of x is equal to x squared. Well, if you square both sides, you just end up with 0 and 1. Okay, so we know from x equals 0 to x equals 1. Might as well put a little 0 there. There we go. Okay, so now we have to figure out which one would be our outer radius and which one would be our inner radius. Well, we can tell from the graph that square root of x is the greater function. So we know that r of x has to be greater than or equal to the inner radius, or the inner radius function. That means for this interval, because you can see if you go outside of that interval, they switch up. But just for this interval, we know that the r of x is equal to square root of x. Well, uppercase r of x. You be a little clearer than that. And and lowercase r of x will equal x squared, since that is the lower function. Okay, so we know that our volume will equal pi times the interval from 0 to 1 of our outer radius squared minus our inner radius squared with respect to x. Okay, so that means our volume will equal pi times the integral from 0 to 1 of the square root of x squared minus x squared squared. With respect to x. Well, we can simplify that a little bit before we integrate. The integral from 0 to 1, square root of x squared is just x. Minus x squared squared is just x to the 4th power. Right. So now we can just go ahead and integrate each term separately and then apply the fundamental theorem. Okay. So the integral of x is just x squared over 2. Minus the integral of x to the 4th power is x to the 5th power over 5. Oh, what up? Dx, duh. And that's from 0 to 1. So now if we apply the fundamental theorem, volume is equal to pi times, we plug in our upper bound. That's 1 squared over 2 minus 1 to the 5th power over 5. Minus, and this becomes 0 and 0, but I'll write it in anyway. 0 squared over 2 minus 0 to the 5th power over 5. Where that just disappears because it's 0 minus 0. So we end up with volume being equal to pi times 1/2, and I'll leave a little bit of space, minus 1/5. Leave a little bit of space after that, because in order to subtract those, we have to have the same denominator. So least common denominator for 2 and 5 is 10, so we're going to multiply this by 5 over 5. Multiply this one by 2 over 2. So volume is equal to pi times 5/10 minus 2/10. Okay, so we have pi times 3/10, which is just 3/10 times pi, you could say 3 pi over 10. Same thing. And clean that up a little bit. There we go. All right. So any questions on that one? All right. If my voice gets a little bit, goes up and down, forgive me. This is like my 5th hour of talking today. So usually about that last hour, my voice kind of goes in and out. So sometimes I try to focus on it to keep it projecting, but sometimes it'll lower just from talking nonstop. So please forgive me if you hear it drop. All right, so let's say, for example, if we wanted to find the volume of the solid formed by revolving the region bounded by the graphs of y equals x squared plus 1, y equals 0, x equals 0, and x equals 1 about the y-axis. So again, when all else fails, if you look at it and you have no idea where you're going to start, always start by graphing. Okay, so we're going to graph everything listed here. So we have our x and our y-axis. So starting off, we have y equals x squared plus 1. Well, y equals x squared is right there on the x-axis. So x squared plus 1 shifts up 1 unit. So we know our y equals x squared is kind of, sort of, somewhat about right there. Now let me make that a little smoother looking. Oops. Ooh. And good enough. Okay, so this is our y is equal to x squared plus 1. Okay, y equals 0 is just our x-axis. X equals 0, that's just the y-axis. Move that down below. And x equals 1, there it is. That's just a vertical line through 1. So if 1 is right here, x equals 1 is just that vertical line right there. And we can actually stop it at the graph. Here we go. And this is our x is equal to 1. So we're going to revolve this around or about the y-axis, which means we're not going to flip it around the x-axis. We're going to get this one and kind of revolve it around this one. Which means there's going to be a little bit of a hole right here, or like a little dip in our volume. Okay. Now we know since we're revolving it around the y-axis, we have to convert all of our equations into functions of y. Since we are revolving about the y-axis, we need our radius of y function, and our inner radius of y function. Remember, this is our outer curve minus our inner curve. Or you could say outer function minus inner function. Okay. So if we look at this graph, and if let's say we're going to spin it around the y-axis. If we spin it around the y-axis, the curve or the function that's going to be on the outside is going to be x equals 1. Okay, so we know that x equals 1 is going to be our outer function. Because remember, the same way we have y is equal to f of x, we have x is equal to f of y. So we can just change that x is equal to 1 to our function of y is equal to 1. Same thing. Okay. Now that y equals x squared plus 1, we have to convert that in terms of y to get our inner function of y. We have y is equal to x squared plus 1. So if we subtract 1 from both sides, we get y minus 1 equals x squared, or just x squared equals y minus 1. So if we square root both sides, we get x is equal to the square root of y minus 1. Okay, so again, x is equal to a function of y, but in this case, since it is our inner function, we know that r of y is equal to the square root of y minus 1. Oops. Now, if you remember, because a lot of times it's a little bit tricky, it seems like it's a little too convenient there, we have to remember that since we had our revolution about the x-axis, that was f of x minus g of x, where this is our region. But when we're revolving around the y-axis,
starting route to 282.51.
we have our outer function, and our inner function. Which is what we're going to revolve around the y-axis. Now, the only thing about our inner function is that that changes for each value of x. Okay, so we see that it's equal to 0 when y is between 0 and 1. Plus, you can tell by the function. Because honestly, you can't make it anything less than 1 because it'll be undefined. Okay, but outside of that y is equal to 1, we know it changes when you go between y equals 1 and 2. It's not a constant between those two values, but it gradually increases. And we'll finish it on the next page. Actually, I can put that one little last note on this one. There we go. Then we'll continue on the next page. Okay, so this means we have to integrate from 0 to 1 and from 1 to 2. And 1 is less than equal to y is less than equal to 2. All right, is anyone still writing? Oh, still writing now. Oh, yeah. All set. Anyone else still writing? All right. Just jot down where we left off. So we know our inner radius is 0 when y is between 0 and 1. And the square root of y minus 1 when it's between 1 and 2. And we know our outer radius is just 1. Kind of, there we go. So we have to keep looking back. I swear, second day in a row, it looks like it's going to rain just as class is letting out. Okay, so we know that the volume is going to equal pi times the integral from 0 to 1 of our outer radius squared. And let me make that parentheses around there. Minus our inner radius squared with respect to y, plus our integral pi times our integral from 0 to 1 times our outer radius squared minus our inner radius squared with respect to y. All right, so we know that our volume is equal to pi times the integral from 0 to 1. Our outer radius squared is just 1 squared. Minus our inner radius squared from 0 to 1, that's just 0 squared with respect to y. Plus pi times the integral from 0 to 1, not 0 to 1, 1 to 2. Why did I repeat that? So it should be from 1 to 2, not 0 to 1. Of our outer radius squared, which is 1 squared, minus our inner radius squared from 1 to 2 is square root of y minus 1 squared. With respect to y. So we know that our volume is equal to pi times the integral from 0 to 1. 1 squared minus 0 squared is just 1 with respect to y. Excuse me. Plus pi times the integral from 1 to 2 of 1 minus the square root of y minus 1 squared. That's just 1 minus y minus 1 because those two cancel each other out. With respect to y. you wanted to, you could have gone from here and just made this 2 minus y, but I didn't want to skip steps. So we just make that pi times the integral from 0 to 1 of 1 dy plus the integral from 1 to 2 of 2 minus y dy. And then we can just go ahead and integrate these separately. So volume is equal to pi times the integral of 1 with respect to y is just y. And that's from 0 to 1. Oh, forgot my pi. So it should be a pi right there. Plus pi times the integral of 2 minus y. We can go ahead and integrate both of those. So the integral of 2 with respect to y is 2y. Minus the integral of y with respect to y is y squared over 2, or you can just say 1/2 y, up to you. 1/2 y squared. And that's from 1 to 2. Okay. So now we have to apply the fundamental theorem to both terms. So our volume is going to equal pi times we plug in our upper bound, which is 1, minus our lower bound, which is 0. Plus pi times, now for this term we plug in our upper bound. So that gives us 2 times 2 minus 2 squared divided by 2. Minus, now we plug in our lower bound, so that's 2 times 1 minus 1 squared divided by 2. Okay, so we know that our volume is equal to 1 minus 0 is just 1, so that's 1 pi, or just pi. Plus, here you have, we'll simplify this first. 2 times 2 gives you 4 minus 2 squared divided by 2 is just 4 divided by 2, which is 2. Minus 2 times 1, which is 2. And actually, we can just drop the parentheses and put it all together so we can avoid doing multiple steps. 2 times 1 is 2. Distribute that, makes it negative 2. Negative 1/2. Distribute that negative, makes it positive 1/2. So negative 2 plus negative 2 is negative 4. So these two, which equal negative 4, cancels out this positive 4, leaving just 1/2. So the volume is equal to pi plus 1/2 pi, or just pi divided by 2. Which you can rewrite as 3 pi over 2. Or you can just say pi times 2 over 2 plus pi over 2, which is just 3 pi over 2. All right. Any questions on that one? Okay, so we're done with 6.2. We will start 6.3 tomorrow. 6.1 and 6.2 are usually the longer sections. We'll probably cover 6.3 and part of 6.4 tomorrow. And we should be able to finish 6.4 by Thursday. All right. So if you have any questions, of course, feel free to ask away. Yes.
The video will be uploaded to the last lecture.
It should be. I have no idea why the last one didn't show up because it's for me. It's showing that it's there.
I don't see it on my side.
Are you using your phone,
No, I'm using my laptop.
laptop? So yeah, that's. Let me check with. Actually, let me write a note now to check with their IT department. All right, you too. Thank you. And I will send them an email right now. All right, thank you. You too. I'll send them an email right now, see if they can perhaps fix it. Yeah. Yeah, you're the second person to say that you couldn't find it, so it's not just you. Yeah. See you tomorrow. All right, you have a good one.
Have a good day.
All right, thank you. You too.